various 2D material platforms. So before this, I'll just give you some background. When we started this work, there were a couple of fundamental challenges, fundamental problems that the world was trying to address, and we thought that let's look into these problems and see what best we can do. Now, what are these fundamental problems? The fundamental problems was, since the discovery of this material, it was very clear that if you cannot make a contact or you cannot interface with the 2D materials or 2D world, you cannot get the current out in layman's term. In other words, if you cannot make efficient contact, you cannot harness the properties that the 2D materials offer. So 2D materials offer a lot of interesting properties, which I'll talk about, but if you want to harness these properties and make use of these properties for real world applications, you need to make efficient contact. If you're not able to make efficient contact, everything is written inside the 2D material, if I put in a simple term. So that was a very fundamental problem that the world was trying to address, both the science and the engineering community. So what we did was we not only understood the science, but we also translated that into technology. That how do you make these interfaces in a more technological viable sense, right? And then how all of that translates into integration inside a transistor. Now, when we did that, as a part of the function of all these investigations, we of course did a lot of work on transistors. And then what we also demonstrated that the limiting factor, which was the contact, when we address that along with the other technological measures, one can achieve record high performance transistors with 2D materials. Now that was one set of problems. The other set of problem was that, which we also found was particularly related to contacts or this interface. So anyone of you who has done basic electrical engineering course would know that in any circuit or what kind of things goes inside the CMOS circuit, you need a complementary system. So you need both N-type transistor, which is an N-type switch, and a P-type transistor, which is a P-type switch. So these are complementary systems, right? So if N-type switch turns on for say X, Y, Z conditions, P-type switch will turn on for minus X, minus Y, minus Z conditions, right? I'm just telling you that it's just complementary conditions under which one would be on and other would be off, and vice versa, right? So now in 2D material, it was not clear how to make a P-type device, though all the devices were turning out to be intrinsically N-type, right? So now, if you have everything which is intrinsically N-type, first of all, you don't know why they are intrinsically N-type. Say, from the basic principle point of view, they should not be intrinsically N-type, but experimentally they all show up as N-type. Second is, if they are all intrinsically N-type, behaving experimentally, then how do you make these P-type devices, right? The complementary device. So that's also something that we discovered that's all related to contact. And when we address that, along with a couple of other things, we were also able to demonstrate, I would say, in real sense, it's going to cost P-type transistors, right? So I'm going to talk about these aspects. Given the hard stop at 5, some of the aspects I may rush. This is not moving. The range. Yes. Okay. I thought range problem. Okay, so quickly I will talk about, I'll quickly run you through what are these 2D materials and what we are working on, why these contacts are important, what the world knew, the quantum chemistry that we explored, or the quantum physics of these contacts that we explored, and once we understand the fundamentals of this, how did we use this knowledge to engineer these interfaces, and how did we use these engineered interfaces or this engineering approach to get to record low contact resistances, right? And also high performance transistors. So a quick summary, most of you, if you are from solid state physics background or condensed matter physics background, you would know what graphene is. But In summary, graphene is the one single monolayer thin sheet of carbon where each carbon atom is hexagonally arranged. This is a hexagonal carbon lattice where each carbon atom is bonded with 3 other carbon atoms. So you have these pi and the sigma bond. Sigma bond here in this case is responsible for the in-plane properties. For example, thermal transport is string. The pi bond is responsible for the electrical properties. Pi bond is outplane. Sigma bond is in-plane. Compared to the conventional bulk semiconductors, the other differential here is that here you have a linear energy relation. So the way particles behave in this system is slightly different compared to how they behave in bulk semiconductor. And if we talk about so graphene was the starting point. Graphene was the small surface. And once graphene was there, people started looking to all other possible materials in their 2D form, and whether they are also dynamically stable. Right. So if I categorize the range of 2D materials, so graphene falls into the family called hexenes. Then you have phosphorines, hexene, all in hexenes family. We work on graphene and phosphorine. Then you have hexanes, and then you have transition dichalcogenides. So these are basically the chalcogens of transition metals like sulfide and selenide of moly and tungsten. And so these are basically semiconductors. And then you have 2D insulators like boron nitride. So what we work on graphene, which is a 2D metal or 2D semi-metal. We work on phosphorine, we work on transition dichalcogenides, particularly these 4 TMDs, and we work on hexagonal boron nitride, which are 2D insulators. And for any practical electronic, optoelectronic device system, all you need is a metal, semiconductor, and insulator. So that was graphene. And if I talk about 2D semiconductors, again in this there are 2 categories, or they can exist in 2 different phases. The 2H phase is the most common phase, which is basically the semiconducting phase, and they can also exist in the 1T phase. And some of the materials do exist in the 1T phase. And 1T phase is the metallic phase where there is no gap between the value and now, why they are interesting? Because of the properties that they offer. For example, if you look into the carrier mobility and electron mobility, for example, is a measure of how fast the carriers would be in a system, right? How efficiently they will move in a particular system, they'll drift in a particular system, right? So if you look into the numbers, what you find is that compared to the conventional bulk materials, the mobilities offered by the 2D systems, particularly graphene and other 2D materials, are either comparable to silicon or better than silicon. Now, what is important to notice here is that when we say comparable to silicon, we are talking about the bulk silicon mobility. But here we have a 2D material, which means it's one atom thick, right? So, but when you compare the thin silicon volume or thin silicon region, the quantization effects kick in, and therefore the mobility of that kind of silicon would be much smaller compared to what we get to the material 2D semiconductor. Right? So one can say that 2D materials certainly offer much better transport properties compared to silicon for comparable scenarios. Right? The other property is that you get a range of optical band. So you can basically tune depending on what material you choose. You can basically tune from the UV spectrum down to IR spectrum, which is something not so easily possible with the bulk semiconductor. That's also something very interesting about 2D materials.
So you talked about this exchange and exchange. The mobility of these exchange and exchange also as high as graphene, or
no, not as high as graphene, but I have to look into the numbers. But I know that graphene has the highest, or among the highest. Hexanes and hexenes, the other ones are not as high as graphene. So, for example, phosphorine is still better than silicon, but not as high as graphene. But I mean, if you compare at those dimensions, right? Say 2 nanometer or 1 nanometer thickness, silicon mobility would fall down significantly, whereas phosphorine would still offer you much better mobility than the bulk silicon That's the reason why they're also quite interesting. On top of that, you have this other optical properties that you can also explore. Okay. So one more thing to add here is that graphene not having band gap basically limits its application in switched applications like CMOS and all, right? But graphene would be interesting for say RF applications or applications where you don't have to turn off the transistor, right? Where it's fine to have the transistors on and you're just modulating the conductivity. Right? So, for example, if I give you compare how much you can scale, say, silicon MOSFET versus MOS2 MOSFET or the TMD based MOSFET, right? So, what it says is the for a given channel thickness, right? I mean, you can go down to say 5 nanometer limit in case of silicon, whereas if it is TMD, you can go down to say 7 angstrom kind of limit. The other advantage is that it's also, I mean, the other properties, for example, which enable the heterogeneous integration, like it's highly flexible, so you can build flexible electronics. You can also engineer the surface, functionalize the surface, so you can basically design the surface for sensing applications. It's sensitive to different volatile organic compounds, and this sensitivity can be engineered depending on the kind of functionality that you do on the surface. It's of course lightweight and mostly transparent, and the light matter interaction in the 2D materials is much stronger compared to pulsing transistors. So that's why they're also quite interesting for the optoelectronic applications. Now that's the reason why the world is pushing for the heterogeneous integration with 2D material, because now in the conventional material, you need different material platform for different applications. Like NEMS would be a different material platform. Right, these chemical, bio, and optical sensors will be a different kind of material platform, right? If you want to build a quantum processor or interlocutor processor, you have a different kind of material platform or technology. If you have a standard conventional memory or CMOS or electronics, it's a very different silicon kind of platform. But with 2D, you can do all of that in the same platform, which means you can integrate everything together on the same chip, right? Which enables the heterogeneous integration that the world has always desired for. So I'll skip this, but the bottom line is that that's the reason why there are worldwide a lot of programs running on 2D material, and we are also trying to now push a big program in the country on 2D material. If you are interested, just do a Google search on India and Bharat some 2D material. It's you'll find a lot of details in the office. Okay. So coming back to graphene, for metallic applications where you want graphene to be used as metal, you compare, say, with copper. And if you compare with copper, again, graphene, for example, outperforms in all aspects, whether it's maximum current that you can handle or the melting point or the tensile strength. Right? So, I mean, of course, keeping all these parameters in mind, if you can handle the technology, the material is sensitive, and I'll talk about that. If you handle the technology, you can certainly build systems which can outperform what currently exists.
In case of copper, you are compared with bulk.
Right. I mean, with the thin film copper, it will be the copper will be even worse. Right. So what else graphene can do? For example, you can build tunable antennas and Terra detectors, particle detectors, and whatnot. I'm showing this not to highlight the application of graphene. I'm showing this to highlight that contacts are important everywhere. Wherever you want to tune the, pretty much most of the things that we see around are some kind of transistors, right? When you are modulating something and you are basically sensing that a change in a property in form of, say, current or light or whatever, right? So if you're dealing with this kind of system, this kind of scenario, you have to contact to study the change or to probe the change or to make the change seen by something else on which a decision will be taken, right? So contacts are important. Contacts are important for everything that you try to build. Now, how the contacts, so that's one aspect, but if I talk about, say, the maximum operating frequency of any system, how the contacts become important, if you see this simple empirical formula, the contacts will be added to the source and the drain resistance, if I just talk about the transistors, right? And that's how the cutoff frequency is inversely proportional to the source and drain resistance. But the contact resistance also affects the transconductance. The transconductance is the rate of change of current as a function of the tuning voltage and the gate voltage. So now this, if you reduce contact resistance by 4 times, you get 4 orders of magnitude change in the transconductance, right? and that goes here. So the cutoff frequency is directly related to transconductance and also related to this contact resistance. So basically, the detrimental effect on the cutoff frequency and maximum frequency of operation is far devastating if you have higher contact resistance, right? And of course, as a function, if you have high contact, you will have a lot of current flowing, you will have one-by-one noise, and all kinds of other effects which will also come into picture because of these contacts. So let's see what the world knew about these contacts. So for example, so this chart shows that what is the quantum limit of these contacts. So when you say quantum limit, the understanding here is that these are two independent systems, right? And you bring two independent systems, non-interacting systems together close to each other, right? And now when you bring two systems close to each other, Fermi together will try to align, and for that, a charge transfer will take place. And when charge transfer takes place, I mean, we are not talking about any chemical bonding or anything, right? We are just talking about two systems which are in the vicinity, so they will be formula alignment, followed the charge transfer will take place. The charge transfer, if the charge both sides is not aligned, and which means there is a charge transfer from one side to the other side, there will be a depletion form, right? In a region whichever is basically transferring charge, and if that region's density state or the strength of charge present in that region is, say, orders of magnitude different than the other, typically not much charge, right? So based on that, I mean, then you know the quantum limit formula for the interface resistance, and then you can calculate, right? Depending on how much charge is present across the two sides, and that maximum charge present across the two sides, assuming that you have, you consider all states in the conduction band are filled, so you have all those charges present, right? So now what you notice is that the graphene and the TMD are two orders of magnitude, 50 times to 100 times higher than what silicon can offer in terms of the contact rates. Right now, this is alarming because if we want to harness the property, if the contact becomes a limiting factor, the actual performance eventually is not going to be better than zero. Right now, again, this is quantum limit based on the semi-classical understanding of how the interfaces are formed. Right, there is no chemical bonding involved. Now, the question that we started asking was, can we break this quantum limit, right? And what we have to do to break this quantum limit, or should there be a quantum limit in these materials, given they are not 3D systems, they are 3D-2D systems, right? So in the beginning, people were trying to, when 2D materials were discovered, when something is discovered, you want to try the conventional effects and apply on a new material system, right? So people tried all the conventional methods, like you heat up the system, you do certain passivations, you do plasma kind of short time scale heating, or maybe you clean up the photoresist that you might have left in the interface, or do some kind of carbon dioxide cluster cleaning in that interface, and try to improve the interface property, right? Ensure that nothing comes between the metal and the system, and improve the contact. So of course, people reported better contact resistance, but that was in relative to a poor interface, right? So basically, you have one side, you have a better interface, nothing in between, and then you have something in between. It's obvious that nothing in between is going to give you a better contact resistance, right? So that was not a scientific advancement. It's kind of an obvious improvement that you would see. So at the same time, the world was also talking about the quantum limit and what kind of contact resistance one can achieve, say in case of graphene, right? So for instance, this number was quoted 162 micrometer. And again, in this case, the fundamental understanding was that you bring metal in contact near graphene, right? And because of the difference in the density state and the amount of charge present, the charge will transfer from graphene to metal, and hence the depletion will be formed. In case of graphene, if you have, say, if you lose 1 electron per 100 carbon atom, you are going to reduce the barrier of 4.4 something, 0.47 electron volt barrier, and that's a big barrier to cross, right? For electrons to move from, electrons to move from the metal to graphene, and that basically introduces the Schottky interface barrier, and hence the contact resistance when you try to conduct, right? Now, what we found was that this concept fails because if this depends on this barrier, Now you know that if I reduce the carrier energy, the carrier is going to see a larger value effectively, right? So if I reduce the carrier, how do I reduce the carrier energy? At room temperature, the carrier has statistically say 25 million pounds and carrier thermal energy which is present in the carrier. If I cool down the system, that energy goes away, which means the carrier is bound to see a larger value, and therefore the resistance should increase. But what we saw and also the world observed, but nobody analyzed it. There were a lot of reports that this is the room temperature contact resistance, the low temperature contact resistance, and low temperature contact resistance was always better. And we questioned that if there is a Schottky barrier theory involved here, then why the low temperature contact resistance has to be lower than the room temperature contact resistance, which should be higher, right? Because I'm taking out the energy from the carrier, I'm just introducing effectively, I'm making the carrier put more effort to cross the barrier, right? So then we also started investigating.
Surface states play any role here? Interface states?
Till the discussion so far?
Yeah.
No, I will come to that. So actually, ideally there are no interface states. This is monolayer graphene. All carbon atoms are fully satisfied. The bonds are satisfied. So there's no dangling bonds. So there's no surface state. So there's no interface state. So now then we also started looking into. So that was our starting point. So we started looking into the bonding properties of metal and graphene. And if there's a way you can make some kind of bonding channel, rather than having a tunneling channel. Schottky interface is like, you don't have a chemical bonding. You have electrons which are passing barrier, and that's how the conduction happens, right? So the initial discussion in literature is fine based on that which metal should be chosen, so that we can reduce that barrier. But we saw it differently. What we thought that, can we basically bring the orbitals present in graphene or say in carbon closer to orbitals present in metal. In that sense, what metal you should choose, which will have closer orbitals having energy states which are closer to each other. Right? I'll talk about this a little later. Let me also highlight this thread, which later when people had shown that the edge contacts are better compared to the top contacts. Right? While no physical explanation was given, the edge contacts were shown to be better, and of course earlier the low temperature contact resistance was shown to be better compared to the room temperature contact resistance. So the physics world moved into the edge contact and doing measurements at low temperature. Right? I mean, I'm fine. We are getting interesting results. We can probe the physics, but the real world is not 4 Kelvin, and the real world is not relying on edge contacts. And that's difficult to make. You can do on 1 or 2 devices, but not in case of large number of devices, millions of devices that you need to build the system. Right? Now, I will pause here on the graphene part, and I'll talk about what the world knew about TMDs and TMD contacts. Right? So, what happens in bulk semiconductor to balance this charge and ensure there is no charge transfer is basically then kind of affects the Fermi level and Fermi level pins. So you cannot have efficient charge transfer, and you have a big barrier built in. So what is done in bulk semiconductor? You basically dope that region. So doping that region means you're increasing mobile charge concentration in that region where you want to make contact. Now, how do you dope in bulk semiconductor? You either diffuse impurities, and this is bulk semiconductor, so there's a lot of volume for impurities to diffuse, or you implant impurities and then activate them through some kind of a thermal treatment or some kind of a annealing process, right? Thermal annealing process. And again, that's bulk, so you can implant, right? But 2D is one atom thing, 1 to say 3 atoms. If it is transition with the dichalcogenides, we're talking about 2 metal systems and 3 metal thickness, right? Say 0.7 nanometer, right? So now you cannot do that kind of diffusion. There's all the diffusion concept which work with bulk semiconductor do not work here. And you also cannot do implantation because where do you implant? It's just one layer thing. It's not a bulk system, right? And again, you don't know what to implant. That's also something which we don't know what to implant, right? I mean, for silicon kind of systems, we know what to implant. For other bulk semiconductors, we know what to implant, what impurity will make this kind of N-type or P-type doping, but here we don't know what they do. Right? So what the world started doing was they started doing charge transfer techniques. And charge transfer means you bring this into in contact with the region, and because of the affinity difference, electron will transfer from one side to the other side. Right? So this is all, you can call it a chemical doping. It's not a stable system, right? So basically, if the chemical is washed off, the charge transfer, when the charge was transferred is gone, right? The charge is not going to stay with the 2D system, right? So there are a lot of charge transfer technique methods demonstrated, and as a function of that, people shown that we can improve the contact. But from technology point of view, you cannot scale it up, right? For example, a lot of salts were shown that pretty much every salt, you dip into that salt, you show that there is a charge transfer, and you have a better technique. So you have low grade, and so the contacts look better. But again, nothing works from a practical standpoint. When you use it for the next process steps, your DI or 3D step, everything is gone. It's washed, right? So that was the status with the 2D semiconductors. Now I'll come back to graphene, and in case of graphene, these were the best numbers reported, and these were all 4 Kelvin measurements, right? But the real world does not work at 4 Kelvin, right? So when we started investigating, we first did certain computations, DFT and GF, to understand these things better, these systems better, and then derive experiments out of it. So what we found was that the edge contributes 40% in terms of the conduction. Now, why is that? So that basically made us thinking that why the edge, where you have very little number of carbon atoms contributing to this conduction, compared to the overlap region, where you have quite a large number of carbon atoms contributing to this conduction, why the edge contributes so significantly, right? Then what we found that in case of overlap region, there is no bond formation, right? So there is no bond formation between the metal and the graphene. Each carbon atom is fully passivated, fully satisfied. So there is no bond formation. So what you have is basically van der Waals force of attraction, and you have a tunneling contact. So that's basically the ideal region or ideal scenario for this Schottky kind of a, right? And the other one on the edges, the carbon atom is not completely satisfied. So we have a bonding kind of a channel, and that bonding channel results in 40% of the electron contribution. If I go back and if you see this point, if I keep increasing the overlap length and force the system to behave more like a Schottky interface, I mean, if the edge is too far from the channel, this system will be dominated by this overlap region, right? So if I keep increasing this, it basically saturates to this 160 ohm micrometer, which was also theoretically predicted earlier as the quantum dimension, right? So now we figured out that you have this bonding channel or the bonding channel based interface of the contact, and the tunneling channel based or the tunneling contact based interface, right? We also studied this as a function of what metals that you choose. So what we looked into was molecular charge, which basically donates the extent of charge transfer in that bond formation. So what we found is that if you look into the edge region versus the overlap region, for palladium there's a difference, and the edge region there's a large charge sharing, which basically donates the bond formation. Whereas in case of the other metals, platinum, you don't have any difference between the edge and the overlap, which means they remain the same. Now the difference here is that this has a 3D orbital, transition metal 3D orbital, which has an energy which is closer to 2D orbital in case of graphene. Right, and that makes the difference. So that basically helps forming this bonding channel. So you need a transition metal which has a 3D orbital, or in general which has say an orbital state which is close to the 2D orbital energy level. Right. So we figured out that you need this kind of PD hybridization for this kind of bonding channel to be formed. And if you can enable this PD hybridization in case of graphene, you can enable these kind of bonding channels, which can improve the contact. The question was how. Now we understand, we know that this is the root, or this is the bottom line. This is what we have enabled experimentally and technologically. But the question is how. I'll come to that point, but let me pause the graphene part, and let me now get into the TMD. So in TMD, what we found, so these are different systems that we studied computationally first. So this is basically, so we studied, all different TMDs, tungsten, sulfides and selenides of tungsten and moly, and we studied for 3 different metals, which are nickel, chrome, and palladium. The most preferred or commonly shown metals in literature demonstrated by right? So what we found, we studied this under again 4 different scenarios. So like 4 different TMDs, 3 different metals, 12 configurations, and 12, and then again these 4 different configurations. So almost we investigated around 48 different configurations computationally first, right? So what is this? So this is pristine, where you have a TMD and you have metal. In this case, we have either sulfur or selenium vacancy created. In this case, we have a sulfur interstitial introduced, and in this case, we have a sulfur interstitial at a selenium vacancy site. So these are the various scenarios that we studied, and they can be realized experimentally that I'll talk about later. Now, I'll skip the details, but what we found that as a function, so again, if you just do the vacancy and the interstitial, nothing happens. So what I'm going to show you is the function of the metal being present on top of it. Just having these vacancies and the defects or vacancies don't change much, right? In terms of what I'm going to talk about. But when you have this metal on top of it, and depending on the metal that you choose, what you get is either you get these donor states or you get certain acceptor states, right? The conduction band closer to a Fermi level is basically you have a lot of donor states. And then you have, if you have, say, a lot of these acceptor states, which brings the Fermi level closer to that, right? So it makes the system p-type, right? So you found that depending on what defect system that you choose, right, vacancy or interstitial, and the metal that you choose, you can selectively introduce these donor states or acceptors, right? So now we knew that we have to deal with certain metal systems and certain interstitials to bring in to introduce these donor states or acceptor states. And again, as I said, in bulk semiconductor, what you do. So you do unity when you do by donor atoms, you create these donor states, right? Which are active at room temperature, so the electrons are transferred to the conduction band. And when you do with the p-type integrity, you introduce these acceptor states, and these will get created at room temperature. So you have a lot of holes transferred to valence. The same thing we discovered that we can do in TMDs by introducing these kind of interstitials and metal, right? So just impurity does not help. Along with the impurity, you also need to bring the right metal into that system. So that's again we studied all these configurations computationally and figured out the molecular charge population, and we studied the transport and figured out the combinations which help us getting that particular scenario, right? So now we know how to engineer, we know what has to be done in case of graphene, we know what has to be done in case of TMDs, right? The question is, how do we realize that experimentally? So now in case of graphene, if we knock out some carbon atoms, we create those sp bonded sites, right? I mean, the sites which are not fully bonded by other, say, 3 carbon atoms, right? Or we can also create these edge states by lithographically patterning that or locally burning certain regions, right? So we further investigated that with computations, and what we found in the presence of metal, in this case palladium, for example, if you see there is a huge density of state increment when we have engineered the contact, which means when we have created these defects, right, these sp bonded sites, or when we have damaged the sp2 hybridization in those areas, and we bring in palladium in contact, we see huge density of state around the Fermi level, and that basically signifies that now we'll have no depletion, we have decent charge transfer. And if you, for this system, right, if you just study the transport across the channel, what you see, the transmission probability does not change, which means no matter what happens in the contact area, nothing changes in the channel region. We are not introducing defect in the channel region, and also the contact area does not influence the channel region. Channel region is intact. That's what we want. We want the intrinsic properties of the materials are harnessed through the channel region. So we want the channel region to be intact. The channel region is not intact, the contact is not, right? So how do we do that? So basically, you have to create these defect sites, right? So one method that we figured out was we can burn locally, regions locally using electron gun. Now, how do you get the electron gun? You have this available in the easy lithography system, right? So you can first develop lithography, you open the contact. You still have photoresist everywhere else except the contact. And now in the e-beam system, you can program, where you want the electron gun to shine high energy electrons, right? And you can program that, so you can basically burn local region, right? So that's one approach. The other approach was you can knock out physically or chemically using argon or oxygen plasma in the contact region, right? The fourth method is we basically pattern or lithographically pattern these edge regions and create more edge regions, right? So we call this form, and we call this RIE, and this is EB, right? So this is a typical TLM test structure where you have graphene and you have these contact pads on the top. It all looks clean because it went through a lot of technological optimizations as well in terms of growth, transfer, photoresist, residue-free, patterning, cleaning, a lot of other things that are also involved in this. That's why it looks great, it looks all clean, looks single crystal. Right. So when you play with the plasma power, we figured out that you can actually play with the different density, and then we use that further for engineering the contact, depositing metal on top. So I'll pause here. So now we know how to create these defect sites, right? In case of graphene. Now we have to bring in these interstitials in TMDs, right, for our contact to work. So how did we do that? We figured out that the H2S actually decomposes at low temperature on top of these TMD surfaces. Now this is very interesting because H2S is the same source that we use for growing these TMDs. So you can actually do this process inside the same TMD chamber inside which you might be growing these TMDs, right? So first level you grow it at different temperatures, and then you bring it back, and under certain optimum H2S flow rate and temperature conditions, they decompose on the surface, and when they decompose, they leave sulfur and the hydrogen. Right? So now the sulfur is staying on the surface, it actually goes and sticks into the interstitial site, and then you can bring metal on top of it and you can make a contact. Now this is more stable because you can do all kinds of process steps afterwards, and the interstitial doping that you're doing does not go anywhere else, right? It stays packed under the metal part, right? So now, and then of course we investigated the system by all kinds of methods, PL, whatnot, to figure out whether the system has changed or not, whether the material has changed or it's still intact. And what we found that the material was still semiconducting, it still gives the same band gap, it is still the same propagation. From experience, we found that now we have extra sulfur present there. From PL, we found that there's a band gap. From gamma, we found that there's no doping without metal being present. No, there was a small change being added to the system, but that's not a concern. Right, so we confirmed all of that, and now let's move forward. So, right, so I've shown you how to create these defects and introduce these interstitials in these systems, right? So as I said, we also dealt with a lot of technological challenges. So these challenges, for example, in case of graphene, is how to transfer large area graphene, and I'm talking about a few centimeters kind of large area graphene being transferred without introducing cracks, wrinkles. So you're growing some copper, you're transferring on a insulating substrate, you have to dissolve copper, you have to transfer it without introducing any crack, without introducing any contamination below the graphene layer. Even water acts as a contamination. Even oxygen acts as a contamination that gets trapped under graphene. And for example, if you have water trapped under graphene and you try to do some high temperature process afterwards, it becomes steam. It tries to break graphene and evaporate it, which means it will damage graphene, and you will not be able to see that water by bare eye or microscope. So you have to deal with all of this, right? Optimize that process, right? Still get high mobility graphene. The other issue is, how do you pattern? So when you pattern, you use photoresist to block certain radiant poles and pattern. Now, when you use photorays, a lot of these photorays have affinity towards this pi bond, right? And if they have affinity towards the pi bond, it would be very difficult to take them out. Either they will tear graphene or they will peel off graphene. After it is patterned, it's a small, it's basically present in form of small islands. So it's very easy to peel it off from the substrate. So how do you deal with that? So we developed this process which was damage-free graphene, and that's why you see the previous picture, which is very clean island of graphene, and that's what you get quite repeatedly. And again, gate stack. So how do you do these insulators for the gate to work? I mean, you cannot grow oxide. Graphene has no oxide, right? It's not like silicon oxide. It can grow. If you oxidize graphene, it becomes carbon dioxide. If you try to deposit anything using methods like TMD, it's ultra smooth surface. We want it ultra smooth. That's what these processes were about. But now that ultra smooth surface, depositing dielectric by ALD becomes highly challenging, right? And of course, contacts and the substrate, the insulator, the other insulating regions, right? So there are a lot of other technological problems that we have to deal with to get to the point where we can say now we have a record high performing device or devices, right? So that's where we build a process step, which involved a lot of things into it. And you can see our devices. This is the P-terminal devices. This is a 200 nanometer channel device. We have a gate. The channel is here. This is the gate. These are all the PLM structures. These are RF devices, right? So now coming to contact resistance. So what we see, we also benchmark with exfoliated graphene, right? So because you see a lot of these numbers report for exfoliated, and I had shown earlier this 200 micrometer or 100 micrometer all exfoliated, low temperature, that's not the real, but the real word is CVD, practical word is CVD, all at room temperature, right? So when you do the exfoliated thing, and as a function of this plasma exposure time, which basically varies the defect density, what you see an optimum point, right? So at an optimum point, you get 100 micrometer kind of contact resistance, all measured at room temperature KA, right? If you measure this in vacuum, you get further betterment in the contact resistance. Now, so that was exfoliated, right? And in exfoliation, if you see the contact resistance without any engineering is close to 1000 ohm micrometer, right? So 700 to 1000 ohm is what people typically used to get with exfoliated material, and for exploring a lot of fundamental properties, this was still okay, right? But if you do the CVD, the same thing becomes 3000 to 4000 ohm micrometer as the CVD, right? But if you do the engineering, it comes down to again 100 ohm micrometer. So when you have this engineered approach, there's no much difference between exfoliated material versus the CVD material, all at the room temperature, right? Now, argon plasma was also tested, and we found it's basically because it's a physical method. No carbon atoms, right? So still you have certain defects present, but possibly you need more to get to that lower number range, right? And then we also experimented all this other like COM shape and the COM plus RI or the COM plus E beam burning, right? And we figured out that at a certain function of this, we are getting the COM plus RI and COM plus E beam, they're giving us the lowest contact resistance around 84 ohm micrometer. Now, this is a little old chart. Our latest numbers with some other metrics are now 36 ohm micrometer. Right. We have not published that, so that's why we have not included that data here. Now, so this is the record low contact resistance that we reported, and even compared to other numbers, this is the record low contact resistance. And now what you see is as a function of different processes, what is the best contact resistance we get. So this is the standard.
Mobility is not affected by this. Because they have paid to make the contact. Mobility is not affected by this.
Mobility gets better.
Is there a logical explanation for that?
Is there
a logical explanation for that?
In principle, it should not get better, but what we measured was the contact limited. So we did not measure the mobility, we did not remove the contact resistance from the data and then try to extract the mobility. But even then, I would say that I will show you the transistor characteristic. And if you see the transistor characteristic, even then it is occurring with the mobility is better. So even if you try to remove the contact resistance effect, the mobility is better. Now, it's a very good question that why mobility is a function of contact resistance. And we have seen this in other systems as well, even in gallium nitride, when we are dealing with a 2D electron gas. We have seen that the 2D electron gas mobility turns out to be functional of the contact. And if you don't have efficient contact, the mobility also appears to be limited. Nobody has answered to this. So it's a question that we are actually looking into at this stage. Okay, so again, as a function of all the engineering methods that we experimented, we got significantly reduction. We demonstrated significant reduction in the contact resistance of the order of 100 ohm micrometer or less. Right. So if I summarize everything that we have seen so far, I mean, I have talked about the SP defect density. That's when you have an optimum required defect density. What you see a V-shaped characteristic, and the V point is the optimum point. When you have low defect density, you have tunneling dominated contact. When you have high defect density, the contact increases because of the current crowding in the contact region. What I did not talk about was that when you have the high contact resistance, there was a big, for example, if you see, there's a big difference depending on the gate bias. But I don't want my transistors, or I don't want contact to be function of the field, the vertical field that is applied, the gate field that is applied, right? Or the gate field based electrostatic doping in the contact area. I want the contact to be ideal, and that should be transparent, and that should behave same no matter what the gate field is, right? But as it shows that there is a big difference between the contact resistance as a function of gate bias when they are not engineered, right? But when you have engineered contact, the difference reduces. The difference reduces, right? And if you also see the variability in the contact resistance from one device to the other device, these are, if I remember correctly, around 40 devices per data point. Right, so the variability also comes down when you have engineered contacts. So again, in this case, if you see the lowest contact resistance also has the least variability, and that's why we chose this for our further transistor level developments and investigations. Right. So at some 100 ohm micrometer, there is least gate bias dependence. And when you have defect engineered contacts, the exfoliated is 3 times lower than CVD. I mean, when you don't have this defect engineering, the exfoliated was 3 times lower than CVD. So basically, the contacts are now also a function of the quality of the material, right? Exfoliated versus CVD. But when you have the defect engineering, the exfoliated and CVD contacts are pretty much same. But the contact resistance are pretty much same, right? And of course, I talked about the organ plasma. And one more thing I've noticed that the difference between the contact resistance and 5 Kelvin also reduced. So when you have a engineered contact, this difference that you measure also reduced, because now it's no more I mean, it's purely depending this bonding channel and not something else, right? And I told you that the E-beam patterning or the oxygen plasma offer the least RC. So this is the comparison. Our record low numbers were 78 ohm micrometer or 84 ohm micrometer, depending on whether it is. Now, this was a separate work which we published in ABL a couple of years back, and what I'm trying to highlight from this work is that the contact. So this is a setup that we built. This is a setup to basically measure transport at nanosecond time scales. We measure down to 2 nanosecond times. And the idea of doing that was to basically measure carrier transport at time scales that are shorter than the thermodynamic time. So we don't want the system to heat up, and we still want to measure current. Now, anything that we measured so far, is all steady state, not DC. Which means we are applying this bias, we are applying forcing the current, and applying voltage for say a few seconds before you integrate and say that this is the value, right? But when you have put the system under stress for that long, naturally you will have a lot of heating present at the contact. So you have by default introduce a lot of or increased phonon population in the contact area, and that increased phonon population is going to affect your transport properties in the contact area, right? So the numbers that we measured so far are with say elevated phonon population in the contact area. So how do we get rid of that? For that, we basically try measuring things at much shorter time scales. So we went down to 2 nanoseconds. And what we found that whatever you measure at the room temperature, this contact resistance drops further when you go to these short time scales. Right? So now the intrinsic contact resistance would measure not only at low temperature but also at lower time scale. That's what we basically figured out and we published in that KPL paper. Now coming back to this thread. So as a function of the contact resistance, the mobility also improved, and that's what I was talking about. And if we had removed the effect of contact, we know that the mobility would have still improved because we have seen that directly in the transistor characteristic. Right. So let's skip some of these details and all, and I'll come to this. So now what you see is a comparison. So this is the standard contact-based graphene transistor, where you see the Dirac point and you see the change in the current. Whereas you see the other one, which is the engineered contact, and you see more of a textbook-like IV characteristic of the graphene device with very nice Dirac point being demonstrated and a significant improvement in the current from this point to this point. So significant improvement in the ion to I Dirac as the contact resistance reduces, as well as significant boost in the current value of these devices, right, for a given bias condition. Okay, so then if you compare our data, which is CVD graphene all on silicon oxide directly, right? Silicon oxide is bound to have a lot more scattering in the channel compared to, say, other dielectrics, aluminum oxide with silicon carbide substrate, right? But what we have is our engineered contacts and, of course, much better technology, or all the technological problems being addressed in a much better way. And what we show is 20% better than what the best was reported so far, that was by IPMD device, right? Now, this is graphene. Let me move quickly to TMDs. So in TMDs, as I've shown, we introduced those contacts. Now, as a function of those contacts, so now there are two things that we did. We basically did introduce those sulfur interstitial in the contact region, and we also tried to use those sulfur. We also tried to use that sulfur for passivating the channel. So now, that was separate, what I have not covered here in the interest of time. What we found that these two TMDs behave intrinsically N-type because of the sulfur vacancy under certain NBM scenarios. So the sulfur vacancies introduce these donor states, and that's why they become N-type. So now, if you have to make it intrinsic, you have to passivate it. You have to passivate the sulfur vacancies. And what we found that the sulfur interstitials that we are trying to bring in, they also passivate the sulfur vacancy. So in the channel, the material does not change if you don't bring the material. So in the channel region, we are only bringing the interstitial, and wherever there is vacancy, to passivate the vacancy, the material is still intact. It's the same channel, same character. But in the contact area, when we break the material, we have this particular new hybridized state, the new bonding channels formed, and better transfer. Right. So now, when we do that, we have increased current, right? And so one case is where we compare with just both contact and challenging. In other case, we compare only with the contact and right. So you see a significant improvement in the current for all different TMDs, no matter which one you choose, whether you take MOS2 or WS2 or MOSC2 or WSC2. In all cases, we have this improvement in the current. Right. We tested this for CVD material as well, and even for CVD material, the technique works. So this was a few layer, and this was monolayer. So the same method works for monolayer as well. And if you measure our contact resistance, the contact resistance, which was close to the so-called quantum limits, say 10 to 5 kilo ohm micrometer, came down to 100 to 50 ohm micrometer. Right? Of course, we also compare all the other transistor parameters, and since the channel was passivated, channel with the contacts get better. All the other transistor parameter, performance parameter, figure of rate parameters are also significantly improved. Now, if you remember, I told you about these donor states and the acceptance states being increased, right? So whatever engineering I did here, these are all using those donor states. Right? So this is all N-type transistor. Now the question is how to make P-type transistor. So now if we choose a different metal along with those vacancies, right? So if you choose chrome, you get P-type. You choose nickel, you get N-type. And that's what we demonstrate here. So when we chose nickel, we get N-type operation. N-type means when you increase the gate voltage in the positive direction, you have conduction. P-type means when you increase the gate voltage in the negative direction, you have conduction. So now we report both N-type and P-type conduction just by changing the metal, right? But having a sulfur interstitial present. If you don't have the interstitial, it doesn't work, right? Because you don't have those lower and acceptor states present. So this brings to the end of my talk. Let me summarize the two threads. On graphene, I talked about the role of sp hybridized sites. I talked about the orbital overlapping ring, which helps significantly reducing the contact resistance. And in case of graphene, I talked about 3 or 4 different techniques to engineer contacts, which allow to improve the scalability of the device and the performance of the device, right? So all the way from contact to the device. If I talk about the contact resistance, we reported record low contact resistance. And in terms of transistor, we also reported better performance compared to the best numbers reported, and that too compared to what was reported for, say, epitaxial graphene on silicon carbide. In case of TMD, I talked about these S interstitials, surface interstitials, and the selected metal atoms. And that introduces these gap states, or these states introduced in the mid-gap region, etc., which are triggered by these the metal and the defects. So these are basically metal and defect induced gap states, right? Which allow you to engineer the orbital overlap or create new hybridized states. And that allowed to engineer the contact, which helps scaling the device and improving not only the contact property, but also significantly the device or the transistor property, right? So in terms of contact resistance, we reported 58 ohm micrometer, which is 400% better compared to any number reported in literature. Transistor performance, we demonstrated overall performance enhancement because not only improve the contact, but also improve the channel property. We passivated those sulfur defects of vacancy, which were making it intrinsically N-type, which we don't want. And we also demonstrated P-channel transistor as a function of the same engineering approach or the orbital overlap. On this note, thank you very much, and I'm open to your questions.
Thank you, Professor Shrivastava. Any more questions?
So, besides this engineering, how would this MXC for this concept?
So we have not explored for MXC, but I would say that the underlying fundamental principle we say that you have to figure out a way that you can make it for this. Now, what is that way? That is something that one has to figure out depending on the system that we're dealing. Like we found in phosphine, it's a different method. But still, the fundamental underlying principle that we are trying to introduce is the same. Right. Graphene is, method is different, but what we are doing is the same. In TMD, the method is different, but what we are doing is the same. Right. So again, for another material system, we have to figure out what we are dealing with in that material system, and then as a function of that, you figure out a way to introduce that. Right.
Yeah.
In TMD, I did not talk about that in the interest of time. We have another paper where we have shown that we actually found a way to implant in TMDs, and that is with fluorine. And we found that with fluorine, you can basically, and again, fluorine and the metal that you choose, you can make N-type and P-type contact. So we have a paper already out, but also months back where we demonstrated all of that, and that was quite interesting. Fluorine not only reduces this donor states, but also reduces certain kind of compressive strain, which further affects the mobility of the channel. Right. So, yeah, I mean, there may be other methods as well that people will discover tomorrow. Right? But the fundamental underlying principle is the same. You basically get fluorine, and again, in that case, we found that the fluorine works only if you have the sulfur vacancies, right? So just introducing fluorine does not work. So you have certain defect states, you bring other kind of infestation, right? And then you bring a particular kind of metal, and they hybridize to form that kind of state, which allows you better electron.
Yeah.
You need to show some RF images of them. So one will like in finite frequency. So how is particular at the contact many these days? Let us take some resistor contact resistance or take capacitance contact RC and parallel.
Well, they still come up as a contact resistance, because even with a Schottky barrier, you get conduction, right? So it's not like you have a pinch off and then you have conduction after a certain point, right? Barrier is not too high, right? So you still have conduction at room temperature, right? So measuring the capacitance of that interface would not be that easy, because you are dealing with a lot of current passing through that interface. What you measure is still the resistance.
There is some capacity that can make some other some unwanted basically.
Just the capacitance at that interface. I mean, the resistive part of the interface will dominate.
One more question.
So in the graphene phase, you showed some that the top phase. What is the gate dielectrics?
So that's what I said. This was not a standard bit dielectric. We built a combination of things that one can grow systematically. I mean, it's being recorded, so I don't want to disclose what it is. But I can tell you that it was not a standard dielectric that we stored it in the LV and stored.
Any other question? Comments?
I can tell you after the recording is stopped.
Okay. Yes, yes. You wanted to stop? I think there are no questions from the.